Okay, this is the fraction review. This is part 3. We have been working on reducing fractions. On this problem, we are asked to write the fraction in lowest terms using the method of prime factors. I'm not going to be checking to see what method you use to reduce your fractions. The goal is to get them reduced. So the methods we've been using, trying to find a number that divides evenly into both of them, that will always work. I'm going to show you another option. By using prime factors, you can see a little bit more of the mechanics as to what's going on in the arithmetic. So what we're going to do is I'm going to show you what we call a factor tree. I'm going to start off with 63. And I want to think of two numbers that multiply to 63, just not 1 and 63. Any other combination will work. Okay, there's a trick to see if something is divisible by 3. Well, we've talked about the rule for 2, and that's an even number. This is not even. It's not divisible by 2. It's not end in a 5 or a 0, so it's not divisible by 5. But what we can do to see if it's divisible by 3 is you add the digits together. 6 plus 3 is 9. Does 3 divide evenly into 9? It does. So 3 divides evenly into 63. I can split this up into 3 times 21. Okay. Now 3 is what we call a prime number again. The only numbers that divide evenly into 3 are 1 and 3. So when you get to a dead end, I strongly suggest that you circle it. That way you know you've ended there. When you get these factor trees get complex, it's easy to lose one. So circling it will help you keep up with it. Now 21 is not prime, so I need to do the same thing again. 21 is 3 times 7. And again, 2 plus 1 is 3. 3 divides into 3, so it works. 3 is prime. 7 is also prime. Now, one of the properties of arithmetic, which is kind of interesting, is that every single number can be broken up to a multiplication of prime numbers. And that multiplication of prime numbers, those numbers are unique. Now, you might get them in a different order, but they will always be the same numbers. So this is unique. I could write 63 as 3 times 7, which I got from here. So 63 can be 3 times 21. It could be 7 times 9 as well. So it's 3 times 7. Now we're going to do the same thing with 1,617. Okay. So I look at this, 1 plus 6 plus 1 plus 7. That would be 15. 3 divides into 15 evenly, so 3 divides into this. But even if I weren't sure, here I could do 1 plus 5, which is 6, and 3 divides into 6. So if 3 divides into 6, it divides into 15. If it divides into 15, it divides into this. So let's just do this. I'm using my calculator. 1617 divided by 3. So if I put a 3 here, this is 539. Okay, so let's see here. 5 plus 3 is 8. 8 plus 9 is 17. That would be, and 1 plus 7 is 8, so I don't have another 3 in there. Okay, let's see if it's divisible by 7. There is a rule for divisibility by 7, but it's so ugly and so hard to deal with. It's easier, even if you have to do long division on paper, it's easier to do it that way. So right here I have 539. I'm going to divide it by 7 and see if something comes up. And I get 77. Why did I choose to check 7? Because there's a 7 in here, and I hope it goes away. Now I'm looking here, and I said that it was a 7. And when I divided it, I got a 77. 77, this is one of the easiest divisibilities to look at. If you've got a repeated two-digit number, it's divisible by 11. And so this is 11 times 7. 7 is prime, so is 11. So I can rewrite this as 3 times 7 times 7 times 11. Now let's look at what we can cancel out. If you have this, these are all multiplications, and that ends up being very important. But if you have the same value on the top and the bottom, you can cancel it out. So I can cancel out those 3s. I can cancel out some of these 7s. I don't have another 3 down here, so I can't cancel it out. I don't have another 7 or 11 up here. So this is just a 3 on the top and 7 times 11 on the bottom. So this is 3 over 77. Prime factorization is not the quickest way to get it done, but it always works, and you can always use a combination of things. If you are dividing by numbers you see in common for a while, and then you still have numbers at the end that you think maybe will reduce further, but you're not seeing how, then you can go to a prime factorization. These things work hand in hand. It's not necessarily one or the other.